The Physics of Interstellar Travel, Chapter 11, Laser Sails. In the previous chapter, we looked at propelling sailcraft using photons from the Sun. Here we extend the idea to propelling sailcraft using much more intense beams of laser light in order to accelerate the sail to much larger velocities. When the sail can be accelerated to a significant fraction of the speed of light, we need to consider relativistic effects. In particular, when a sail is receding from the laser at a velocity beta, in units of the speed of light, the photons reflected off the sail are Doppler shifted to lower frequencies, that is, redder wavelengths, by this equation. As lower frequency photons have less energy, this tells us that some of the incident photon energy has been transferred to the sail. This equation also shows that the faster the sail, the more energy is transferred from the incident photons to the sail. Understanding this involves some slightly subtle, although not complicated, issues of relativity that I discuss in the chapter. Using conservation of relativistic momentum and energy, we can derive the velocity of the sail as a function of the energy provided to the sail. We find that the velocity depends only on the mass of the sail, m, and the total amount of energy received, EL, but not on how that energy has been received, for example, whether steadily or in variable bursts. This plot of the equation shows, for example, that by the time the sail has received an energy equal to its mass, E equals mc squared, so a value of 1 on the horizontal axis, then it will have been accelerated to 0.8 times the speed of light. For a 10-gram sail, this corresponds to 250 gigawatt hours of energy. Looking more closely at the photomechanics, we can derive an equation of motion for the sail. For constant laser power, this gives the acceleration in terms of the power, PL, the sail mass, M, and the reflectivity and absorptivity of the sail, given by R tilde and A tilde. Solving this equation, we can plot the variation of the sail's velocity with time or distance. This figure shows how the velocity varies with time for a perfectly reflecting 10-gram sail propelled by an enormously powerful 100 gigawatt laser. We see that after just 19 minutes, the sail is moving at 0.2 times the speed of light. This figure on the right shows how the velocity varies with the distance. By the time the sail is moving at 0.2 times the speed of light, it has travelled nearly 0.25 AU, 37 million kilometers, from the laser. Because it takes a finite time for the photons to travel from the laser to the sail, then at a given time at the laser, not all the photons emitted have yet reached the sail, even when we consider the same rest frame. We must therefore be careful when we define concepts such as efficiency, which take into account this time. So far, we've assumed that the light emitted from the sail reaches the laser eventually. But in practice, diffraction will spread out the beam significantly, and some of the laser light will spill around the edges of the sail. The diffraction angle alpha, shown here, is of order the wavelength divided by the laser aperture diameter, dt. So for a wavelength of 1 micron, when the laser light is sent by a telescope with 10 meters diameter, this angle is 0.1 microradians, or 20 milliarcseconds. From simple geometry, we see that this angle is also equal to s over a. When the sail is at a distance of 0.1 astronomical units, this diffraction angle corresponds to a size s of 1.5 kilometers. Even an extremely light 10-gram sail, like the one we just considered, would be no more than a few meters in size, and so almost all of the laser light will spill around the edge of the sail. Thus, with a 100 gigawatt laser power transmitted by a 10-meter telescope, most of the laser light would never even have hit the sail, and the sail's velocity would be far below the value that we just calculated. We therefore need to use a much larger telescope aperture in order to reduce this diffraction angle. Increasing the aperture by a factor of 100 would reduce the radius of its diffraction pattern to 15 meters, which still involves quite some loss of power when the sail is far away, but this may be manageable. The problem, though, is that we can't build a monolithic 1 kilometer telescope, and it will probably never be practical to do so, not even in space. But we can instead use a technique known as aperture synthesis. If we imagine taking a large mirror and then chopping small bits out of it, we can create a beam with a diffraction width similar to that of the original large mirror. Now, this is not practicable as a large telescope because to ensure that all the beams remain in phase, we would have to move the mirror segments up and down to keep them in the right places as the telescope points in different directions. However, we can get around this and keep all the mirror segments in a common plane if we instead use variable delay lines attached to each mirror segment. These ensure that all the beams travel the same distance so that we get a coherent wavefront. Aperture synthesis is routinely done in astronomy for very low power incoming light, and this figure shows incoming wavefronts. Synthesizing apertures when we have extremely intense outgoing light brings along new challenges. There are also complications arriving from the Earth's turbulent atmosphere distorting the outgoing beam. This could be addressed, as it is in astronomy, using adaptive optics, but again, this has not been done with these very high power lasers. I discuss this and some other challenges in the chapter, as well as the advantages and disadvantages of putting the laser array in space to avoid the problems with the atmosphere. Let us briefly consider the sail itself. 100 gigawatts is an enormous laser power to be focused on a sail that is only a few meters in diameter. Unless the sail is either highly reflective or has a very high melting temperature, it will simply be vaporized by this enormous intensity. The metal films considered for solar cells are not reflective enough, and the melting temperatures are too low for them to be used in laser sails. Better candidates are dielectrics, which, although less reflective, have much higher melting temperatures. Examples include zirconium dioxide and silicon nitride. Recall that a sail could also be propelled by the absorbed photons. Graphene is a single layer of carbon atoms which is extremely light and strong with a high melting temperature. It has almost zero reflectivity, and normally its absorption is quite low too, although doping it can increase this. It's a promising material, although the maximum photon intensities it can theoretically tolerate are still far below that we need for small sails. A more promising avenue might be a two-dimensional photonic crystal. This is a thin layer of material with a regular grid of micron-sized holes that have a diameter not much less than their separation, so most of the structure is in fact holes. This design reduces its mass. But because the hole sizes are on the order of the laser wavelength, and because they have a regular structure, the material acts like an optical grating that uses constructive interference to increase the material's reflectivity. There are several other issues I have not mentioned that I discuss in the chapter, such as sail stability and combining lasers. I also examine a few designs for both small and large sails that have been proposed in the literature. There are still many hurdles to cross before laser sails become a reality. These include building powerful lasers and large telescope arrays, and developing ultralight reflective or absorptive materials with very high melting temperatures. But laser sails are one or two plausible options that we have for getting to the stars quickly, the other being fusion rockets.